Yeah, so my topic today is microscale thermal fluid engineering for energy applications. So yeah, so I think for this community, I don't need to emphasize why thermal fluid engineering is really important. We use this for electronics thermal management. We can also use this for desalination, water harvesting, and recently in the pandemic, right, we see how respiratory droplet evaporate, how they transport, and even how does the sunlight affect the virus. It has something to do with heat. And in today's talk, I would like to mainly talk about two stories. First is how we use thermal fluid engineering to manipulate multi-phase fluid in terms of how can we control a single bubble and single droplet. And the second story, the second half, I would like to tell you a little bit about our understanding about how temperature affect batteries and how, a lot of the degradation or failure mode in batteries is actually introduced by temperature. How can we, what exactly is the fundamental cause and how can we mitigate that? And so to start, phase change heat transfer, this is something that, many of us work on, for example, right, we have pool boiling, we have flow boiling. And in the past, I've mainly worked on microchannel heat sinks where we engineered microstructured surfaces on the heated wall of a microchannel. And so the surface can, this microstructures is really able to help facilitate a wetting film on the heated surface to prevent dry out or delay dry out. And in condensation, right, it's hard to put everyone's work here, but I've selected Nat and Dan's work. And we've seen, right, being able to manipulate jumping droplet or being able to achieve dropwise condensation for low surface tension fluid, we are able to see enhancement of heat transfer coefficient. And so in all of these boiling condensation, we know that droplet and bubble departure and removal is really important. In boiling, right, if we do not let bubbles to leave the surface, we let the bubbles to accumulate on the surface, it causes CHF. However, similarly, right, in condensation, if we don't remove the droplet, condensate droplet fast enough, this can cause flooding, and that leads to heat transfer degradation. And so, interestingly, I would like to just show you two more examples. One is pool boiling in microgravity. So I don't know if this video can play, but on Earth, right, on the left is on Earth. You see once you have boiling, you see many small bubbles generated, and they leave the surface easily due to buoyancy. But without buoyancy in the space, right, when you generate a bubble, the bubble becomes stagnant on the surface, and they just grow, accumulate, merge, and grow into a giant bubble. And so that's why the pool boiling performance in microgravity is worse than what you would typically expect on Earth. And last, this is I also want to say that bubble dynamics is extremely important in electrocatalysis. This is slightly out of outside phase change heat transfer, but this is multi-phase fluid systems. So when you think about electrocatalysis, right, that we have water splitting to produce hydrogen fuel or oxygen, right? We have, we also have you consume a gas, so you can remove CO2, use electrocatalysis and turn CO2 gas into a value-added product. And for example, in gas producing in reactions, if how you treat your substrate is really important. If you have a substrate that is kind of a little bit hydrophobic, so that any gas that's produced, any gas bubbles, right, get stuck to the surface, you see a much worse performance. Versus if you look at the bottom right figure, right, if you kind of have a super hydrophilic substrate where any gas bubble you generate, when they're still very tiny, right, they're able to depart the surface, you see a much better performance. And I think this figure of merit in catalysis is really similar to the boiling curve, where you have a flux on the y-axis. This is what you try. Well, so the magnitude of that flux is what you're trying to maximize. And the x-axis is like a superheat. So this is the potential. This is called the over potential. So the extra potential you need to pay for compared to the thermodynamic potential. So I think this is really interesting, but you can see again in all these systems, being able to depart bubble or remove droplet is really important. This is what we want. And so, so after I started at UCSB, I've been thinking, is there any dynamic way method that we can manipulate droplet and bubbles? So, okay, so to really, if we talk about dynamic method, right, there has been a lot of work to dynamically manipulate droplets, motions and bubble motions. And for example, a lot of the methods have used surface microstructures or micro nanostructures on the surface. And if you can dynamically tune those micro nanostructures, you may be able to manipulate the fluid. So in this example, we fabricated a magnetically tunable micro-pillar arrays. And so they can actually tilt and move in a magnetic field. And so if you you can also coat the surface, you can do wettability coatings to control its wettability. But a simple example is when you put a droplet on such a surface, by just tuning the external field, you can tune where the droplets spread. And so, however, if you look at many of the magnetic papers, current, the major limitation is that usually we need a really, really high magnetic field. So this is a little bit less practical and easy to implement, not easy to implement. On the right-hand side, there's also electrowetting on dielectric. And this has been really successful. And even for a lot of microgravity applications, this has been shown to be really successful. So we're all familiar with electrowetting, right? So by controlling the voltage on a droplet on a insulated electrode, you are able to control the contact angle. And this has been really handy to transport droplet on the surface. You can also do what's called a digital microfluidics, where you have an array of electrode. So you could do simple things like merging two droplets and splitting two droplets. So in this case, this is a droplet, you're splitting it. And however, right, in electrowetting also, the main limitation is that usually you need hundreds of volts. You need a really high voltage. And so this is subject to, there's concerns over longevity and what if the dielectric layer breaks down. So that led to a few recent really nice works that's using ionic surfactant and as well as localized heating. So ionic surfactant are those surfactants that are, they have, charged head or charged tails on the surfactant. So basically they can be charged. And so then you can basically apply an electric field to attract or repel those surfactants to a substrate. And we all know that surfactants are great to changing the surface tension or tuning the surface tension. So on the bottom left figure, you can actually, by patterning, several electrodes, you can actually control where boiling occurs by controlling the surface tension. And more recently, C.J. Kim's group kind of explored this idea a little bit further. So they actually used these ionic surfactant to realize digital microfluidics. So you could do a lot of complex fluid manipulations, such as merging, splitting, all the things we mentioned before. But using these two methods, although you still need electric field, you only need like 2 or 3 volts, really low voltage. So that's really a big advantage. And also there's a recent interesting work by 𝗘𝗴𝗆𝗀𝗀𝗆 where you can actually use lasers to drive a bubble on a surface. So this is try my best to explain the mechanism, but I think the main mechanism is that you utilize localized heating in their system. You can also add nanoparticles to enhance plasmonic heat absorption, basically, and then you apply the laser on one side of the droplet that can create a heating effect and that allow droplet to move on a surface, or in this case, bubbles. So we've been thinking, so these latter two methods are really, they have their advantages. So we've been thinking, can we combine them to achieve a, manipulation, kind of microfluidic manipulation platform that's easy and also does not require high voltage or high laser. I want to mention that, this laser localized heating, you do need a relative high laser energy. And so our approach is that we selected these light sensitive surfactants and to manipulate fluid. And so what are those light sensitive surfactants? They basically are surfactant that's specially engineered with usually a tail group or head group or some molecules on the surfactant that can go through a conformation change when you illuminate the surfactant with a light of a particular wavelength. So in this cartoon, right, if I have a surfactant A in conformation A or A isomer, if I shine light on it, it will transform to another type of conformation of the surfactant. And so, and this is reversible. So if you remove the light, and the surfactant reversibly switch back, or this switching back process can be accelerated by shining a light of another wavelength. This is really handy because when you add a little bit of surfactant into a fluid system or fluid interfacial system, the surfactant, they tend to like to accumulate on the interfaces. And by just shining light to the system, you are able to dynamically tune the surface tension of your system. And so this is handy because you can actually use this phenomena to do droplet departure or bubble departure, and as well as droplet sliding. Or I think it has potential to do digital microfluid as well. So the mechanism for departure is that, for example, I have a bubble or droplet in another fluid. Right? And I shine light to asymmetrically to one part of the droplet. So in this case, right, if I shine light to the top part of the bubble, light one, so right, my top part is B surfactant rich, right, B rich in B type surfactant. So you have one surface tension that is sigma B. But if I make sure that the bottom is dark, or if I want to further ensure that I have A type surfactant, I can shine light to the bottom of the droplet. So you see this, you have the surfactant gradient, concentration gradient, or surfactant, they have different types. And then as a result, you have a surface tension gradient and you induce a Marangoni flow. And if your external is a fluid phase, you have fluid on the outside. But if you have droplet and droplet, you have this interfacial flow in both phases. And as a result, this interfacial flow will basically generate a net force on the bubble, causing it to depart the surface. And I took mention that in this case, we want the interfacial flow to flow from the top to the base, such that it kind of squeezes the bubble away from the surface. Likewise, you could do sliding on the surface by also applying light to only one side of the droplet. And this work is in collaboration with Professor 𝗘𝗴𝗆𝗿 and Professor 𝗵𝗨 at UCSB. And so, so how do we design the surfactant, right? There's actually a lot of photosensitive surfactant already been developed. So I'm not a chemist, so I tried best to explain. So the biggest, the most important characteristic of those photosurfactant is that we want the surfactant to change, to introduce a large change in the surface tension. And so that can be done by having a surfactant that goes through a very large polarity change. For example, right, it can be amphiphilic in the beginning, and when you shine light on, it can lose its amphiphilicity. And so you can imagine the surfactant kind of switch between a more hydrophobic surfactant to a more hydrophilic surfactant. And so Javier basically, they selected by looking at a lot of different types of surfactant. They basically they engineered this surfactant called SPDAPEG, and these types of surfactant display a really large polarity change, and it's activated by UV light, and you could reverse the reverse reaction is basically can happen spontaneously in dark, or it can be accelerated in with visible light. And so that's really, really handy. So we use this 𝗵𝗲𝗿𝗂𝗃𝗃 surfactant, and you can, what's neat about the surfactant is that as it goes through the transformation, as it goes through the switch, it also has a color change. So that allows you to visibly see, I've introduced a switch. And so this is before switching, and we have this 𝗵𝗲𝗿𝗃𝗃 surfactant, I believe, in water. And so when you turn on the UV light, right, this is UV-LD, it is transparent, but suddenly it will become pink. And so you could then, use a UV LED lamp to illuminate the entire region, so the entire region becomes pink. And then you could use white light, or we just remove the UV, right, to change this back. You could see that when we turn the white light on, immediately the region illuminated by the white light become clear. So then you could switch it, the entire phase system back. And so how about the surface tension, right? So this is the interfacial tension of water in air. And with a little bit tiny amount, I believe 0.1 millimole surfactant, 𝗵𝗲𝗿𝗃𝗃 surfactant. So you can see that, we want to see whether you can have a very fast response. Right, so when you turn the UV on, turn UV off, you could see surface tension changing back and forth. I'd like to mention that this is measured by a pendant drop method using a commercial tensiometer. And so this pendant drop method is not really ideally suited to measure the equilibrium surface tension of a system with surfactant, because of the time scale of surfactant to travel, absorb to the interface. That would take some time. But nonetheless, right, in a lot of the systems, we care about what happens dynamically when you go induce a change in the system. So we want to see what happens in the first few seconds, not really the equilibrium surface tension. But we can, of course, just turn on the light, turn off the light for long enough time and see where, see what the final state is. You can see that this is, again, water. And you may recall that water has a surface tension of 72, right, normally. And usually adding surfactant will lower the surface tension, and that's indeed what we see, right? So adding surfactant, your surface tension becomes 47, 46, but then when you turn the light on, the surface tension increased by 254, 55. And you can notice that we only used really, really low intensity UV light. So these are less than 1, right, milliwatt per millimeter square. So these are a lot lower intensity compared to even a laser pointer. You could induce this fast change. I would like to say that for this particular liquid system, you can see that when you turn the UV off, the back reaction is a little bit slower than the forward reaction. But again, you can accelerate by turning visible light on. So our next question is, can we really depart a droplet, right, in another system? So this is kind of a little bit challenging to do with liquid gas interface because of buoyancy, right? Buoyancy will naturally want to depart a bubble. So we selected our first system to be a fluid system. So in this example, we have water on the outside, and we injected a toluene, which is a common solvent, that's insoluble with water, so into the system. And again, right, we want to see, how does this water toluene interfacial tension changes with the light. So we measured that again. So when you turn the UV light on, right, this interfacial tension actually drops. And in this case, that's a 20-30% drop. That's a very big change in the surface tension. And when you turn off the UV, it moves back. You could go this many cycles. And so we designed this kind of experiment where we focus a UV laser beam just on top, right, close to the top part of a toluene droplet. You can see that, right, as soon as we turn on the laser, you immediately see a light change. You could see the path of the laser because the surfactant become pink. So you could see that region where that's the pink region, and that immediately caused interfacial flow, and that caused the droplet to depart. And the departure time from the moment we turn on the laser till we actually depart the surface is only about less than 0.4 second. So this time scale is still, right, it's fast, right? It's almost instantaneous, but to really use this for boiling, we may need to, further increase this time scale, because at least for boiling on Earth, right, we're talking about time scale of, tens of milliseconds. However, I do believe that this may be interesting for space applications where, bubbles, they tend to grow to a much bigger size and they do not depart the surface, right? So this time scale may be suitable for space applications. But again, right on the bottom right is that we show time lapse of this dynamic process where when you turn, for example, right, in a control experiment, when we do not turn the light on, in both clear water or in a system with no surfactant or in a system with surfactant, right? If we don't turn the light on, the droplet will be pinned on the surface. But as soon as we turn the light on, right, you see this light beam that, immediate change of color, and that color kind of travels down because of Marangoni flow, right? And then departure. And so we're very excited about this. So not only you can do droplet departure, but also you can tune the, you can change the position of the light to actually pin the droplet on the surface. And so in the top figure, we have just a very low intensity UV LED, about 0.5 milliwatt per millimeter square, right? Really low intensity. You focus that onto the top part of the droplet. And so that reduces the local surface tension. So that causes a Marangoni flow downward in the outer phase, or in both phases, the Marangoni flow is downward. And then you would have a net upward force on the droplet. And so that will basically facilitate droplet departure. But you can also move the light to the bottom of the drop, right? Now you lower the surface tension of the bottom of the drop, which is not good because, which again help the fluid, the bubble to depart, because now the pinning force is smaller. But in terms of the Marangoni flow, right, the fluid is now traveling from the bottom to the top. That Marangoni flow help to pin the bubble on the droplet. And so eventually the bubbles still depart, because in this situation, right, you actually reduce the pinning force on the bottom surface. But you compare the two cases, the time required for the droplet to depart, right? The UV LED on top cases, you can reduce the departure time by an order of magnitude, right? So this indeed suggests that, right, in these two systems, the Marangoni flow, basically they can play a role in tuning the departure time of a droplet. And so again, this is toluene in water. We finally moved on to test air bubbles in water, and you could see that, right, we inject an air bubble in a water with surfactant with this 0.1 millimole toluene surfactant. So this is, yeah, sorry, this should be toluene. So sorry about my typo right here. This time, right, we used again a very low intensity UV LED, and we just put the LED right on top to see what happens, right? The LED is, as long as we don't use a laser, which is collimated, right? LEDs are naturally diverging, so you have a naturally changing intensity of the light. So that imposes light intensity gradient on the droplet, and you can then have a surface tension gradient. And so again, you could see that when we don't have the light for the first two cases, right? So this first two cases are surfactant of SP isomer, that's surfactant A, right? And the MC is after it completely switched. When we don't have the light, you need the droplet, the air bubble needs to go to a size of 4 microliter to depart when buoyancy becomes, overcome the pinning force. But when we have the light turned on, you can reduce the departure. So the droplet, the air bubble grow to a smaller size before it's able to depart. And further, when you turn the green laser pointer on the bottom, you can further, I think this is a very tiny enhancement. So we are actually still working on how can we maximize or how can we optimize this departure process. But you can see the comparison when you turn the light on, when you don't turn the light on, you have a change in the departing volume. And so So that's about our droplet and air bubble departure. We think this could be helpful for microfluidic applications and potentially will be helpful for boiling. How about condensation, right? Before I talk about condensation, right? The next question we ask ourselves is that, how big are those forces, right? How big are those Marangoni forces? So when you can first do a order of magnitude or scaling analysis. And for example, when you have an air bubble on a substrate, right, the buoyancy, so this is FB is the buoyancy, it scales with the bubble diameter to the third power. And you have also the pinning force due to surface tension at the bottom of the base of the bubble. And when you have a surface tension gradient from the top of the bubble all the way to the bottom and the base of the bubble, right, in terms of delta sigma, the Marangoni force you can induce is proportional to delta sigma and also the length scale of the bubble. And for example, if I do this manipulation on Earth, I want the photo-Marangoni force to be at least 10% of the buoyancy, right? I want this to help with the buoyancy to depart the bubble. Then the required surface tension change, sorry, again, I guess I used gamma in this. The required surface tension change has to be higher than 0.1 times, G delta rho and dB. So dB is the departure diameter of the bubble or droplet when there's no photo-Marangoni force, right? Just when buoyancy balances the pinning force. And so this is the required surface tension change. However, right, if you're in microgravity, completely no buoyancy, you want the bubble to depart, you want to have the photo-Marangoni force to completely balance the pinning force. The required surface tension change becomes this relation, right? Delta gamma needs to be greater than the gamma times. It's also dependent on the contact angle, right? So a more hydrophilic surface, it would be naturally easier to depart bubble, even when we add the photo-Marangoni force. So what really happens for this departure of these toluene bubble, right, in water, is that we also performed detailed finite element simulations. So on the top left, this is a toluene droplet in water with low surface tension, low concentration of the surfactant. And so when we turn the light on and on the top side of the droplet, you can see this is the velocity, or not the velocity. Yeah, so this is the velocity distribution inside and outside the droplet. You can see the streamline, right? You indeed introduce these interfacial kind of flows from the low surface tension to the high surface tension region of the droplet, right? And to verify that, right, we actually added tracer particles into a droplet. You could see, right, droplet particles move upward from the center and they move downward from the bottom. And so this kind of validates, right, you do have these secondary flow inside the droplet and outside the droplet. Not only that, but we also modeled the pressure distribution. You can see that, right? So the external pressure is will exert an external force on the bubble, right? So if you look at the external pressure distribution, you see that you see a high pressure region near the base of the bubble. So this pressure actually also help to as a result of the Marangoni flow, right, will also help the droplet to depart from the surface. So both the interfacial viscous shear, right, this interfacial flow will have a shear force on the droplet. So both that viscous shear and the pressure, they contribute to the droplet departure. And you can actually calculate the force as a function of the distance away from the base of the bubble. You can see that, right, PZ is the pressure. So the pressure is really high at the bottom, at the base of the bubble, but then it become negative. So at the center of the bubble, the pressure become negative. So that region actually pressure will pin the bubble on the surface. But again, this is a really small magnitude compared to the really high pressure on the base. So still the net pressure will, the net direction of the pressure is upward. right? So this 𝗬𝗪 is the viscous shear. You can see that viscous shear is almost always positive, which is pushing the droplet upward, right? Departing the droplet. So the net force again is, as a function of the z-axis, is mostly right positive and maybe a little bit negative on the end of the droplet. And with that, right, you can further calculate how, if I vary the surface tension change, right? This is the change of surface tension. How does these two forces change, right? You could see that when you have a larger surface tension change, the viscous force, both the viscous force and the pressure force increase, right? And on the right-hand side, we also calculated the net force, including the pinning force on the droplet. And you can see you want the net force to be positive, meaning that the direction of the force is away from the substrate. So it's departing the droplet. And so you could see that in this situation, right, in this particular toluene water system, we needed a surface tension change of at least 23–24% for the net force to be positive, right? Again, I think this photo-Marangoni kind of manipulation platform can be potentially used in boiling, pending that we figure out the time scale. But we're hopeful that this will be a really interesting platform for microgravity applications. And we think that this can potentially also be useful for electrocatalysis and other microfluidic platforms. And so moving on, I think many of you have been wondering what happens to droplet, right? We actually also tested a droplet. And this video shows, right, we have a water droplet, and we put the droplet on a porous Teflon substrate infused with Krytox. So this can be, liquid infused porous surface. And we want the surface to, of course, to be, highly mobile. So in this video, right, we added an optical filter. So one side of the optical filter, it is transparent to light. On the other side, this is dark. So then we just added, we turn on a UV lamp from the top. And so you have naturally create a light gradient. You can see again, right, when you turn the light on the droplet, basically naturally you can move from the lighter, more stronger light region to the dark, right? You move into the dark. And, we also perform simulation. Again, you see those interfacial secondary flow inside the droplet. And what's really helping the droplet to travel is on the bottom, right? You have low surface tension fluid flowing to the higher surface tension region, and the external Krytox flow, right? Also, you have that shear, you have the interfacial flow. So that shear kind of exert a net force, causing the droplet to move towards the right-hand side. So with this validated, right, you could do a lot of fun things. So first of all, right, you could let the droplet to move from bottom to top, and then you can change its moving direction from right to left. And so this is we're looking top down, looking at, and you could use this by a UV laser. And you can also help two droplets to merge, right? You can have two droplets on the surface, and you can then move one of the droplet to towards the other droplet. And you could imagine this as a very neat or platform for chemical reactions, right? Very controlled chemical reaction. And what's neat with light is that you do not need to pattern electrode, pre-pattern electrode. You don't need to do any fabrication. You just need a laser pointer. And these light pattern, you can draw any pattern as you want. You can reconfigure them very easily. But nonetheless, right, if you want to have a pre-configured light pattern, you could do. So our student also kind of come up with this. This is a UV LED array. I don't know why it appears bright, but this is UV. And you can kind of program the light, right, to run any patterns. And so hopefully we're still in the test of this droplet, but the idea is that you can use this light to then manipulate droplet to run different patterns on the substrate. So with that, I'd really like to kind of wrap up this first, and I think there's a lot of opportunity in condensation. because we know that droplets condensation has been possible, proven to be possible for a low surface tension fluid when you have a condensation that's occurring on a slip surface or Liz surface, right? So we think that you can conventionally you need to tilt the substrate, you need a gravity, right? You need to shed those droplets due to some sort of force. But I think, right, in this situation where you can simply shine light on the droplet, right, the droplet may be able to spontaneously move from one side to the other side. And this will be, again, very interesting for microgravity applications where there's no buoyancy, there's no gravity at all. And you could also do digital microfluidics. Hopefully you could do digital microfluidics, right? I showed you a very fun video of digital microfluidic. This is realized by electrode wetting, right? So you do need to pre-pattern those electrodes and apply voltages to these droplets. But I think that with light, there's a lot of potential. You could reconfigure the light. There's also, right, with light, you can have very high spatial resolution. So I think I'd like to wrap up the first story and then quickly move on to talk about batteries due to time. Batteries are actually, I think this is a really important problem, and that's worth our thermal community to investigate, to look into, right? Because there's thermal issues in batteries, and so far, right, we don't understand. We don't even understand how microscopic temperature impact battery very well, right? Of course, when you have shorting, when you overheat the battery, that can be catastrophic, right? You can cause fire, explosion, and in this image, right, you could see this is an infrared image of a battery with internal shorting inside. You can see the battery explosion process. Not only is thermal process important for the safety of batteries, but nowadays, right, as we advocate for fast charging, there's extreme fast charging. So the concept being charging a battery of electric vehicle to within 15 minutes, right? Within 750 seconds. And so in a simulation by Unreal, they've actually shown that when you don't consider the thermal management of those extreme fast charging battery packs very well, the temperature of the battery can exceed 300 degrees Celsius, and that's never a temperature you want the battery to operate at, right? You can cause catastrophic decomposition of the cathode, releasing oxygen, and that can catch fire. Also, right, when we build bigger and bigger volume batteries with higher capacity, and when you do fast charging and discharge, batteries generate heat, and these heat need to spread out, well, from the center region to the boundary of the battery first, and then get dissipated, right? So you can build up a temperature gradient inside a battery, and that's important because electrochemical reactions are very sensitive to temperature, right? So you can have very high temperature, and that causes very high current. And low temperature region, you have low current. That causes a heterogeneity of charge and discharge within batteries, and that's also not good. Right? So these are the motivations for us to really understand how temperature impact batteries. There has been a lot of previous work trying to understand, how a uniform temperature impact batteries. And this is a little bit straightforward to do, right? You throw the battery into a very, very well-controlled temperature environmental chamber. You run the battery at different temperatures, and you see what's going on. You can see normally, right, people have found that the higher temperature, right, the faster the capacity of the battery fade. But as you go to the lower temperature, right, you begin to see defects forming, right? In this case, a dendritic lithium dendrite forming on the lithium electrode at low temperatures. And you can also envision lithium plating, right? At really low temperatures, the slow kinetic will cause lithium ion to plate on as a lithium metal on a graphite anode instead of intercalating to the graphite. So there's a lot of nice work to understand how a uniform temperature environment impact batteries. But I think for a modern understanding, right, in reality, battery can, as I mentioned, can have a temperature heterogeneity due to internal heating or due to how you cool the battery, right, external cooling. you can also have localized hotspot within batteries. And when you have a large capacity battery, how the battery electrode is contacted to the external circuit is through a tiny pad, contact tab. Right? This contact tab, you have localized Joule heating, and these are the region that's also shown to be the first place to kind of cause degradation and cause shorting. And so then you can maybe have some local defect that causes battery to kind of internally short. And that can also cause a temperature hotspot to form. So in all those modern kind of situations, we really need to understand how a microscopic temperature distribution impact batteries, and that's less understood. And so the challenge is really due to it's not easy to measure the temperature of batteries, especially at the microscopic level, right? So conventionally, you can use thermocouples to measure the external surface of batteries, but that doesn't tell you what's happening on the electrode level inside the battery, right? You can use IR imaging. IR images are usually limited to tens of microns spatial resolution, so you can't also get down to the spatial resolution required for battery electrode, which are less usually battery separators are usually only 10 microns thick, right? Or single particles can also be a few microns big, right? Or you can simply drill a hole and you can drill a hole, insert a thermocouple, but then this is destructive. We don't want that, right? And I think there has been really nice work from the thermal community trying to kind of work on this area. So in 2014, Professor David Cahill's group, they used pump probe to actually probe the thermal conductivity of a lithium cobalt oxide, so which is a common cathode material for lithium-ion batteries. You can see that during charge and discharge, they reported a 35% change during partial delithiation of lithium cobalt oxide. And so you can actually use this right to actually know what's happening inside the battery, because if I measure a thermal conductivity change, I know that this material is lithiated or delithiated. So that's exactly that kind of lead to this really recent paper just a few weeks ago by 𝗵𝗵𝗿𝗀𝗇 group, where they used a very simple method. They added 3 omega sensors onto the external surface of a battery electrode. By measuring the thermal conductivity of graphite anode, they are able to know the distribution of the heterogeneity of different lithiation process inside the graphite, which is extremely important because we want the battery to be uniformly charged or discharged. If you have heterogeneity, that is almost always the first reason that can cause lithium plating or any defect to occur. So this is really clever. Simply by measuring thermal conductivity, they are able to map out, they are able to tell what is the SOC state of charge distribution. So we are kind of inspired by Cahill's work, where we think, using optical, some platform that's optical, right? You can allow you to maybe measure the temperature inside a battery and see how temperature impacts batteries. And again, so we choose Raman spectroscopy. So the advantage is that you can have a very high spatial resolution down to 1 micron, easily down to 1 micron, right? With surface enhanced Raman spectroscopy, you can even have a higher spatial resolution. And then you can also use laser as a heating at a heat source, right? And then you can use the Raman spectrum to know the temperature. So how it works, right? You have Raman light laser shining on a sample, and so the photons can actually absorb or emit a phonon, and so the backscattered photon, right, will have a shift in its frequency, and that shift is temperature dependent. So you can use this to measure temperature. And so what kind of system, right? We immediately think lithium metal battery would be an excellent model system to study, because lithium metal battery is really considered the highest, lithium anode, right? It really has the highest specific capacity, right? So this will be really attractive, much higher than the current lithium-ion batteries. However, this has not been commercialized because lithium metal has really uncontrolled growth. Well, we want the lithium metal to be growing really well, right? Ideally, when we are charging our our battery want lithium ion move from the cathode to the anode, and they deposit on the anode. You want the lithium metal to grow very nicely. But in reality, you always see this, right? That you see lots of dendrite forming. These lithium metal can crack. They can also pierce through the separator, causing shorting. So, a lot of work have focused on understanding why lithium metal have uncontrolled behavior and how can we control the growth of lithium. And we think that there's really not a angle from a temperature perspective. So our question is, what would a temperature hotspot do to the lithium growth? So we basically put a lithium metal working electrode under the micro-Raman spectroscopy. We can use laser to create a temperature hotspot, and then we can also measure the temperature of the hotspot. So the only thing we did is we added a graphene layer to on the backside of the working electrode, because lithium metal itself does not have Raman signal. So we needed something as a Raman signal, as a probe to tell your local temperature there. So just really quickly, right, you see that very nicely, as I mentioned, the Raman shift of a lot of material is temperature dependent. So we can calibrate this temperature coefficient, the slope of the Raman peak versus temperature. You can then use this information to measure temperature for different laser powers. As we heat, right, we increase the heating power. In this case, it is a bit extremes, right? You can create a temperature hotspot over 100 degrees Celsius. Right, so we also did thermal simulation, but here's the interesting result. So when you have a perfect battery, right, when you deposit lithium metal onto the anode, when you have the rest of the battery is at room temperature, but when you have a temperature hotspot in the center of 50 degrees Celsius, you see more lithium metal on that temperature hotspot. Right, when you increase the temperature to 80 degrees and 99 degrees, right, this becomes more severe, right? You have lots of lithium growing on the temperature hotspot. In this extreme case, you don't really see any lithium metal on the other region. You only see them almost all on the temperature hotspot. So you see that temperature can introduce significant non-uniformity of lithium growth. And so to really understand why, right, we modeled the diffusion of lithium inside the electrolyte, as well as the reaction of lithium redox on the electrode surface. And we found that temperature basically impact the reaction more severely, right? So this really enhanced kinetic at higher temperature is really causing the local over deposition of lithium. And again, right, you may argue that, this is kind of intuitive, because a higher temperature, you should expect any reactions to occur faster. You wouldn't see this for a uniform temperature battery, because again, right, the temperature is uniformly the same everywhere. So you still have the uniform deposition. This only occurs when you have a non-uniform temperature. You will see a spatially non-uniform deposition of lithium. And so again, we modeled the system. You can see that not only it is non-uniform, but you can see the bottom three figures. This is the lithium plate current density, how much lithium that's being plated on the lithium electrode. You can see that by having a temperature hotspot of 100 degrees Celsius, you can induce a 300 times more lithium plating, 300 times compared to the background, which is controlled at 1 milliamp per centimeter squared, right? So I'll try to wrap up so quickly. And I think this is really important, because normally when we think about battery failure, we think about, battery is somehow shorted, maybe by mechanical impact, and that shorting caused some heat to be generated inside the battery, and that caused thermal runaway. But I think our basic study basically tells that shorting and hotspot is not one way, right? It's not a one-way relationship, it's a double-way relationship. So if you have a non-uniform temperature inside battery, this can potentially cause non-uniform chemical reactions, and that can cause shorting, potentially cause shorting. And so, yeah, so our question is, can shorting actually be triggered by a local heating event? And the answer is yes. We simply did this very simple experiment where we have a battery, right? We use laser to create a temperature hotspot of about only 40 degrees Celsius. You can see then as we run the battery, apologize for the video to not play, but as we charge the battery, so you could see a lot of lithium plating right? I don't know if I play this right now, it'll play, but you will see a lot of lithium plating only on the hotter temperature region. So apologize for the video, but and basically it showed that by having a warmer spot, you can trigger shorting at that warmer location. We also measured that temperature response of an internal shorting by adding a resistance temperature detector right next to the spot where we're using a mild laser heating, right? You can see that as in the first kind of 300 seconds, the battery is charging normally. But because we're heating that location, right, that location has a big lithium chunk that quickly causes internal shorting. So after the internal shorting, the temperature sensor is able to capture the immediate temperature response after internal shorting. And at some point, we had to shut down the battery for safety reasons. But again, this is the first study that can actually monitor the local temperature response during at the electrode level during an internal shorting event. And so moving beyond that, right, we studied the lithium metal battery. I'd like to quickly mention there's a lot of opportunities for other materials, like graphite, for lithium ion battery, silicon anode, and even sodium anode for grid scale storage, grid scale energy storage, right? There's also lots of cathode materials. People don't understand the degradation mechanisms very clearly right now. So there's lots of opportunities. I'd like to mention that we first look at kinetics, right? Temperature actually also influences the thermodynamic of batteries as well. So let me tell you an example, right? For lithium ion battery, normally when you charge and discharge, you want the lithium ion to move back and forth between anode and cathode. And so we call this insertion chemistry. So this is a normal mode, right? In almost a lot of the abnormal situations, you have lithium ion moving from the cathode during charge. And instead of intercalating into the graphite, the lithium ion plate as lithium metals on the substrate. And you can see, right, this is graphite anode, you have lithium metal. And that is really bad because that causes, the lithium metal can pierce through the separator, cause shorting. You also lost capacity fade. So there are lots of concerns. And so people have thought, when you do fast charging or when you charge the battery at low temperatures, that will cause the sluggish kinetics, right, at low temperature will cause the anode potential to drop below the equilibrium lithium potential. That causes lithium plating to be more thermodynamically favorable. So this has been the current understanding. But what we think that, right, what if you have a temperature non-uniformity inside a battery, right? And the temperature can potentially impact the equilibrium potential of this lithium plating. So if that shifts with temperature, you can totally have maybe a region inside the battery with a lithium plating potential to be higher than the anode equilibrium anode potential. That can also trigger lithium plating to occur. So that's indeed our hypothesis in this schematic cartoon is that, right, when you have a, cylindrical batteries, right, you have a very large electrode area. And when you unwrap the electrode, right, you can totally have a room temperature region and a warmer region, right? So, and so if that temperature influences the equilibrium potential of lithium, which is drawn in this slope right here, right? This equilibrium potential of lithium, you can, as a result, you may have a region in the warm region. If this potential is increasing with temperature, right? That region potential can exceed the anode potential. That means now in this region, it's more thermodynamically favorable for lithium to plate as lithium metals in this case, right? Instead of intercalate into graphite. And that is exactly what we see, right? So we measured the temperature coefficient. Indeed, the potential equilibrium potential of lithium increase with temperature as we increase the temperature, right? About 1 millivolt per Kelvin. And then we did a very interesting experiment where we added a thin film platinum heater onto the backside of a graphite anode, and we control the heat such that the hotspot, right, this mid-center region is only about 50 degrees Celsius, and so and then we charge the battery, right, normal charge rate, not even high fast charging, and when disassemble the battery, we immediately see a lithium metal in the center region on top of graphite. And we made sure that when we charge our battery, right, we made sure that the anode, the macroscopic, right, anode potential is always below, is always above lithium plating potential. So this lithium plating is not caused by anode potential, right, dropping beneath the equilibrium lithium potential at room temperature. This is really caused because of the locally warmer temperature that shifted the lithium potential to be greater than anode potential. And so this is also the first study that shows that instead of having a temperature, colder temperature, right, you need to, warmer temperature can actually cause lithium plating. So apologize, I need to wrap up really quickly, right? So I think there's a lot of opportunity to really understand how temperature from our thermal community, how temperature impact batteries, and from measurement, characterization to modeling. And so with that, right, just a little bit of ongoing work, we're trying to use, a variant of Raman spectroscopy, which is called the surface enhanced Raman spectroscopy, that really can give you chemical composition change during cycling at the electrode interface, right? This is only a few nanometers thick that can really give you the nanometer resolution and that can give you more chemical information compared to a normal Raman spectroscopy. You can see those peaks you wouldn't see with a normal Raman spectroscopy. We're also looking into how can you see 3D structure of batteries using MRI, right, magnetic resonance imaging. So the idea is that you can have lithium metal and you can see them under MRI, and now you can then create different temperature, heating, cooling scenario and see how does that impact to the 3D morphology of lithium, and potentially use this for 3D temperature mapping as well when you add temperature probes into your system. So with that, I really like to thank for your attention. I think I have time for tunable microfluidics and batteries, and hopefully in the future we can tell you about our work on other things over time.